Welcome to Hafi Sleep, my curious friends. Look up. Go on, just for a second if you can. Look past the glare of the streetlights, past the familiar branch of that old tree outside your window, past the thin, fleeting clouds. Look into the deep velvet black, at that one stubborn pinprick of light that seems to have been watching you your whole life. Now, imagine that star has a family, planets, and on one of those planets, a rock not unlike one you might kick on a walk, and under that rock, maybe, just maybe, something is stirring, something that is not us. That question, are we alone, is perhaps the oldest, most profound, and most thrilling we have ever asked. It's a whisper in the cradle of civilization, a shout from the launch pads of Cape Canaveral, a silent prayer we send skyward on a clear, dark night. It's a question that can make you feel incredibly small and yet, paradoxically, part of something unimaginably vast, all at the same time. Today, we're not just going to ask that question. We're going to live in it. We're going to unpack it, from the tiniest, most resilient microbe to the grandest visions of interstellar empires. We're going to sift through the science, the myths, the math, and the pure, unadulterated wonder of it all. We are going to hunt for aliens, not with spaceships and ray guns, but with our minds. So, get comfortable. This is not a short story. This is the story of us and the possibility of them. To even begin, we have to understand the stage, and what a stage it is, the universe. It's a word we throw around so casually, but let's try to feel its weight for a moment. Our home, Earth, is a planet orbiting a star we call the Sun. The Sun, that brilliant life-giving ball of fire, is just one of perhaps 100 to 400 billion stars in our galaxy, the Milky Way. Let's just sit with that number for a second. Not 1,000, not 1,000,000. Billions. If you were to try to count every star in our galaxy, one per second, it would take you, well, over 3,000 years. And our galaxy, the Milky Way, this colossal spinning disk of stars, gas, and dust so vast it takes light 100,000 years to travel from one end to the other, is just one of hundreds of billions of galaxies in the observable universe. The numbers are so large they cease to be numbers and become more of a feeling of dizzying, humbling, awe-inspiring scale. Now, let's shrink that down to something we can almost grasp. Imagine the entire history of our planet, from its fiery birth 4.5 billion years ago to you sitting here, right now, listening to this. Imagine that entire timeline compressed into a single calendar year. Imagine that calendar hanging on your wall. It's a big, beautiful calendar, with each month representing roughly 375 million years. On January 1st, at the stroke of midnight, Earth forms. But it's nothing like the blue and green marble we know today. It's a terrifying place. The surface is a global ocean of molten rock, constantly churning and bubbling. There's no atmosphere to speak of, just a suffocating haze of vaporized rock and toxic gases. The sky, if you could stand there to see it, would be a dull, angry red. This is the Hadean Aeon, named after Hades, the Greek god of the underworld, and it's a fitting title. It's a world under constant bombardment, as the leftover debris from the solar system's formation, asteroids and comets, rains down in fiery apocalyptic impacts. One of these impacts, by a Mars-sized body nicknamed Theia, is so violent it blasts a huge portion of Earth's material into orbit, where it will eventually coalesce to form our moon. So the moon is born from this chaos, a silent companion created in violence. For the entire month of January, Earth is a hellscape, slowly, painfully, beginning to cool. As we move into February, the planet's surface starts to solidify into a thin, fragile crust. The bombardment slows, but it's still a violent place. Volcanoes are everywhere, spewing out gases like water vapor, carbon dioxide, nitrogen, and methane. This slowly forms the first, very primitive atmosphere. There's still no oxygen. It's a poisonous soup. And then, deep in the oceans, perhaps near a hydrothermal vent on the seafloor where mineral-rich, superheated water gushes out from the Earth's crust, or in a warm, shallow pond somewhere, something miraculous happens. We don't know the exact date, we don't know the exact location, but according to our calendar, it happens around February 25th. A collection of non-living molecules, stirred by chemistry and energy, arranges itself in a way that can make a copy of itself. This is the spark, the first life. It isn't a creature. It isn't even a cell as we know it. It's likely just a simple, self-replicating strand of RNA, a cousin of DNA, wrapped in a protective fatty bubble. It's the humblest, most unimpressive beginning imaginable, but it is the most important event in our planet's history. The universe on this one little rock has become alive. For the next 8 months, March, April, May, June, July, August, September, and most of October, nothing much seems to happen from our human perspective. The planet is dominated by these simple, single-celled organisms. They are called prokaryotes. They have no nucleus, no internal organs. They are just tiny bags of chemistry. But don't be fooled by their simplicity. They are the pioneers, the ultimate survivors. They evolve and diversify, learning to harness energy in different ways. Some, the archaea, thrive in these extreme environments, in boiling water and acidic pools. Others, the cyanobacteria, discover a trick that will change the entire planet forever: photosynthesis. They learn to use sunlight to make their own food, and in the process, they release a waste gas that is toxic to most other life at the time: oxygen. This is a slow-motion catastrophe for the ancient world. Oxygen is a highly reactive, destructive molecule. It rusts metals. It breaks down other organic compounds. For billions of years, the iron dissolved in the oceans has been slowly settling to the seafloor. Now, as oxygen begins to build up in the water, it reacts with that iron, causing it to rust on a planetary scale, creating massive bands of iron ore that we still mine today. This goes on for millions of years, the entire ocean slowly rusting, until the sea can't hold any more iron. Only then does the oxygen begin to leak into the atmosphere. This is the Great Oxygenation Event, and it's the first and perhaps most severe mass extinction event in Earth's history. The oxygen-poisoned atmosphere wipes out vast swathes of ancient microbial life that cannot handle this new, toxic gas. The world is forever changed. The sky, once a hazy orange, begins to turn blue. We're now deep into our cosmic year. It's November. The planet has a new atmosphere, rich in oxygen and nitrogen. The stage is set for the next great evolutionary leap. And it happens again in a moment of incredible cooperation. One simple cell engulfs another, but instead of digesting it, they form a partnership. The engulfed cell becomes a permanent resident, an energy factory. This is the birth of the complex cell, the eukaryote. These cells have a nucleus, a command center, and organelles like tiny organs. This symbiotic event is so crucial that every single plant, animal, and fungus on Earth today is descended from that first fortunate merger. Life is no longer just a solitary cell. It's now a collaborative venture. Now things start to speed up. By early December, these complex cells have learned to stick together, forming the first multicellular organisms. We see the first worms, the first jellyfish, creatures so soft they leave almost no fossils behind. Then, around December 15th, life undergoes an explosion of creativity. In a relatively short period of time, in the oceans, almost every major body plan we know appears. This is the Cambrian explosion. We see the first creatures with shells, with eyes, with legs. The oceans are suddenly teeming with bizarre and wonderful life forms, like the alien-looking Anomalocaris, a predator the size of a lobster with bizarre grasping appendages and eyes on stalks. It's a wild evolutionary experimentation. Life is thriving in the sea, but the land is still a barren, rocky desert. That is, until around December 20th, when the first pioneers, lichens, and mosses begin to cling to the rocks at the water's edge, slowly, over millennia, breaking them down into soil. They are followed by the first plants, which transform the landscape, creating the first forests. With plants come the first insects, scurrying among the roots and leaves. The world is turning green. And now, we finally approach the day we've all been waiting for. It's December 25th, Christmas Day. In the wake of another mass extinction, a new group of animals begins to rise to prominence. They are the dinosaurs. For the next 4 days, they are the undisputed rulers of the planet. They are not just the giant, long-necked sauropods browsing the treetops or the terrifying Tyrannosaurus rex. They are also the birds. That's right, the birds are dinosaurs, the last living descendants of that mighty lineage. They fill every niche, from the colossal to the tiny. The world is loud with their calls and roars. They dominate the land, the sea, and the air. This is their era, and it seems like it will last forever. But the universe has a way of reminding us of its power. On the evening of December 29th, a visitor arrives. An asteroid, perhaps 6 miles wide, traveling at over 40,000 miles per hour, slams into what is now the Yucatan Peninsula in Mexico. The impact is beyond comprehension. It releases more energy than 1 billion nuclear bombs. It triggers mega tsunamis, global firestorms, and blasts so much dust and sulfur into the atmosphere that it blots out the sun for years. The world plunges into a long, dark, freezing winter. The dinosaurs, along with about 3/4 of all plant and animal species on Earth, are gone. It's all over by the evening of December 29th. Their 150 million year reign ends in a single catastrophic day on our calendar. This sets the stage for the survivors. The small, furry, shrew-like mammals that had been scurrying in the shadows, hiding from the dinosaurs, now emerge into a world emptied of its giants. With the dominant predators gone, they begin to diversify, to grow, to experiment. December 30th and 31st are the age of mammals. The world sees the first whales, the first elephants, the first primates swinging through the trees, and now the clock is ticking down to the end of the year. The final day, December 31st, is the day of the hominids, our direct ancestors. At around 1:30 in the afternoon, our lineage, the Australopithecines, like the famous Lucy, are walking upright on the savannas of Africa. They are using simple stone tools. The sun begins to set. At around 11:30 p.m., Homo erectus has mastered fire. This is a monumental step. Fire provides warmth, protection, and, crucially, cooked food, which provides more energy and helps our brains to grow. The final hour of the final day is a whirlwind. At 11:52 p.m., Homo sapiens, that's us, are painting on cave walls in places like Lascaux and Chauvet, creating art, expressing abstract thought. At 11:59 p.m., just 1 minute to midnight, we invent agriculture. We stop being nomadic hunter-gatherers and start to settle down, building villages, then towns, then the first civilizations. All of recorded history, the pyramids of Egypt, the Roman Empire, the Great Wall of China, the Renaissance, the Industrial Revolution, the discovery of penicillin, the World Wars, the moon landing, the invention of the internet, you being born, you listening to this right now, all of it, every single moment, fits into the last 60 seconds of this cosmic year. Let that sink in. On the scale of our planet's history, all of human civilization is a single minute. A minute filled with glory and tragedy, with love and war, with discovery and folly. We are so new. We are the freshest of fresh arrivals. Our world, which feels so ancient and permanent to us, is, in cosmic terms, a very recent development. We are living in the last few moments of the very last day of the year. This perspective is not meant to make us feel small or insignificant. Quite the opposite. It's meant to fill us with a sense of wonder and possibility. Look at how much has happened in all those slow, patient months leading up to us. The universe spent billions of years preparing the stage, building the atmosphere, creating the complex cells, weathering extinctions, all leading to this fleeting, precious moment where a species emerged that could look back at the universe and ask, how did I get here? And is anyone else out there? We are the universe's way of becoming conscious of itself, and we've only just opened our eyes. And with that humbling, exhilarating thought, we are finally ready to begin our search in earnest, to step out from our tiny speck of time and look at the immensity of space with new eyes. So when we ask, are we alone? We are asking if, in this unimaginable vastness of space and time, with hundreds of billions of galaxies, each with hundreds of billions of stars, life in all its forms has only happened here. On this one tiny, fragile world, in that one fleeting second of cosmic time. It seems statistically improbable, doesn't it? It feels almost arrogant to think we could be it. This simple, powerful idea is the heart of what's known as the Drake equation. It's not a strict formula you solve to get a definitive answer, but rather a way of structuring our thinking, of breaking down this gigantic question into more manageable, bite-sized pieces. Formulated by astronomer Frank Drake in 1961, the equation is a series of factors we multiply together. It starts with the number of stars born each year in our galaxy. That's a big number. Then we multiply it by the fraction of those stars that have planets. For a long time, we didn't know this. We assumed planets were common, but we had no proof. Then, we multiply by the number of those planets that are in the Goldilocks zone. Not too hot, not too cold, but just right for liquid water to potentially exist on the surface. Then, the fraction of those planets where life actually does arise. Then, the fraction where that life becomes intelligent. Then, the fraction where that intelligent life develops technology we could detect, like radio signals. And finally, the length of time such a civilization releases those detectable signals into space. You see the problem? The first few factors, stars with planets in the habitable zone, we're getting good data on now, thanks to telescopes like Kepler and TESS. They've shown us that planets are not the exception, they are the rule. Most stars have them, and a good fraction of those are rocky worlds in the habitable zone. So the universe seems to be teeming with potential real estate for life. But it's the next steps where we plunge into the unknown. How often does that potential become reality? How easy is it for life to spark from non-life? This is the mystery of abiogenesis. Let's travel back in time to that young, violent Earth. It was a hellscape. Volcanoes spewing lava and gases, no oxygen in the atmosphere, a constant bombardment from asteroids. It seems like the last place you'd expect life to begin, but it's precisely in this chaos that the magic happened. To understand how, we need to think like chemists, but without the complicated formulas. Think of it as a cosmic kitchen, and we're about to bake the very first, most primitive cake of life. The first thing you need are the ingredients. And the universe, it turns out, is a well-stocked pantry. The prime ingredient, the flower of life, is carbon. Why carbon? It's a social atom, a bit of a flirt. It has a unique ability to form strong, stable bonds with many other atoms, including itself. It can form long chains, intricate rings, complex branching structures. It's the Lego block of the universe. You can build an almost infinite variety of molecules with it. Other atoms are more aloof or form weaker bonds, but carbon loves to connect. So, we have our carbon. Then we need the other staples: hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These are all incredibly common elements, forged in the hearts of ancient stars and scattered across the cosmos when those stars went supernova. We are, quite literally, made of stardust. Now, imagine these raw ingredients just floating around in the early oceans and atmosphere. They're simple molecules like carbon dioxide, CO2, methane, CH4, ammonia, NH3, and water, H2O. On their own, they're inert. They don't do much. But a kitchen needs an energy source to start the baking process, and the early Earth was brimming with energy. It was a world of constant, violent cookery. You had the intense ultraviolet light from the young sun pouring down unimpeded by an ozone layer. You had massive, world-shaking lightning strikes crackling through the thick, primitive atmosphere. You had the relentless heat and chemical richness from countless volcanoes and, crucially, from those deep-sea hydrothermal vents we mentioned. These vents are like natural pressure cookers on the ocean floor. They spew out a superheated, mineral-rich broth from deep within the Earth's crust. They are not just sources of heat. They are also intricate structures full of nooks and crannies, and most importantly, they create a gradient, a difference in temperature and acidity between the vent fluid and the surrounding cold ocean water. This gradient acts like a battery, a natural source of power that can drive chemical reactions. It's in environments like this, or in those sun-drenched tidal pools where water evaporates and concentrates the ingredients, that the simple molecules began to get to know each other. Driven by all that energy, the lightning, the UV light, the geothermal heat, these simple molecules started to bump into each other with more and more force. They began to link up, forming more complex organic molecules. Organic in this sense just means carbon-based. We're talking about amino acids, which are the building blocks of proteins, the workhorses of life. We're talking about nucleotides, which are the building blocks of nucleic acids like RNA and DNA, the information storage systems of life. For a long time, this was just a theory, a compelling idea. But then, in the 1950s, two scientists named Stanley Miller and Harold Urey decided to test it in their lab. They built a closed glass apparatus, filled it with what they thought the early Earth's atmosphere and oceans were like: water, methane, ammonia, hydrogen, and then they zapped it with electrical sparks to simulate lightning. After just a week, they looked inside. The water had turned a murky brown, and when they analyzed it, it was teeming with amino acids. They had created the building blocks of life from simple, non-living ingredients. It was a stunning result. It showed that the step from simple chemistry to the basic components of life is not a monumental leap, but a relatively small, almost easy one given the right conditions. So the soup was getting richer. The oceans of early Earth were likely a dilute broth of these organic molecules, what's often called the primordial soup. But a soup of ingredients isn't a cake. You need a recipe. You need something that can bring these molecules together in a specific way. And most importantly, you need something that can copy itself. This is the leap. This is the moment of abiogenesis. The leading character in this drama is most likely RNA, or ribonucleic acid. You've probably heard of its more famous cousin, DNA, which is like the master blueprint of a cell locked safely in a vault. RNA is like the photocopy of a single page of that blueprint that gets sent to the workshop to tell the machines what to build. But RNA is much more than just a messenger. It's a shapeshifter, a molecular Swiss Army knife. Here's the incredible part. RNA can do two things that are absolutely essential for life. First, it can carry information, just like DNA. Its sequence of nucleotides is a code. Second, and this is the magical part, certain types of RNA can act as enzymes. They can catalyze or speed up chemical reactions. We call these ribozymes. And guess what one of the reactions they can catalyze is? The copying of RNA itself. So you have a molecule that is both the instruction manual and the photocopier. Can you see how powerful that is? Imagine one of these RNA molecules forming by chance in the primordial soup. It's just a random sequence. But if, by sheer fluke, its shape allows it to help link nucleotides together, it might start assembling other bits of floating RNA, creating copies of itself. They wouldn't be perfect copies. Mistakes would happen. And those mistakes are what we call mutations. This is the dawn of evolution. Now you have competition. An RNA molecule that is slightly better, slightly faster, slightly more stable at copying itself will soon outnumber the others. Natural selection, the driving force of evolution, begins at the molecular level before there is even anything we would recognize as life. This hypothetical early stage of life is called the RNA world. It's a world where simple, self-replicating RNA molecules are the dominant form of life, evolving in complexity over millions of years. Eventually, these RNA molecules would have learned to build protective containers around themselves, primitive cell membranes made of fatty acids, which naturally form bubbles in water. This was a huge step. Now you have a distinct entity, separate from the outside soup, protecting its precious self-replicating machinery inside. Later, RNA likely enlisted the help of proteins, which are better at doing jobs, and eventually figured out how to store its information in the more stable double helix of DNA. RNA, the versatile pioneer, handed over the long-term storage duties to DNA and the day-to-day work to proteins, settling into its role as the messenger. The first true cell was born. So, was this a freak accident? The Miller-Urey experiment and countless others since tell us that the building blocks form easily. We find amino acids and nucleobases on meteorites. The Murchison meteorite that fell in Australia in 1969 was loaded with them. The ingredients are universal. The conditions, water, energy, a planetary surface, seem to be common on rocky worlds throughout the galaxy. And time? The universe has had 13.8 billion years. Earth is 4.5 billion years old, and life appeared here surprisingly quickly within the first billion years, as soon as the planet had cooled enough to be remotely habitable. This suggests that, far from being a 1 in a trillion event, the emergence of life might be a natural, almost inevitable outcome of the laws of chemistry and physics, given the right environment and enough time. It's like having a trillion boxes of Legos, and in every box you shake it for a billion years. The chance of a specific complex model appearing might be tiny, but the chance of some kind of self-replicating, interesting structure appearing in at least one of those boxes. That starts to look almost certain. The universe has been shaking the Lego box for a very long time, and it has a lot of boxes. So, while the journey from that first self-replicating RNA molecule to a complex cell like a bacterium was long and arduous, the first step, the spark of abiogenesis, might be a relatively common flicker in the quiet, dark corners of the cosmos. This doesn't diminish the miracle of life. It magnifies it. It suggests that the universe is inherently creative, that it has a bias towards building complexity, and that we, far from being a solitary accident, are most likely part of a vast and still silent family of life. But let's be clear, when we say life, we are often, in our minds, picturing little green men or sleek gray beings with large dark eyes. But the vast majority of life in the universe, if it exists, is almost certainly not like that. It's microbial, it's slime, it's mats of bacteria. For over 3 billion years, that's all life was on Earth. Simple, single-celled organisms. They are the true rulers of this planet, and they would likely be the true rulers of any other living world. So, the first and most likely signature of life we might find will not be a radio signal, but a gas. This is the exciting field of biosignatures. Imagine we point a powerful, next-generation telescope like the James Webb Space Telescope at a distant exoplanet, a planet orbiting another star. We can't see continents or oceans from that distance. It's so far away that even with our most powerful telescopes, it's less than a pixel on a screen. We can't see clouds, we can't see land masses, we can't see city lights. It's just a speck of light. So how in the world can we possibly guess what's happening on its surface or in its air? The answer is, we don't look at the planet directly. We listen to the story its light tells. It all comes down to a beautiful and powerful technique called spectroscopy. Now that might sound like a complicated word, but the idea is beautifully simple. Think of it like this. Every element and molecule in the universe has a unique fingerprint. Not a fingerprint you can see with your eyes, but a fingerprint of light. When light from a star passes through a planet's atmosphere, the gases in that atmosphere leave their unique fingerprints on the light. Imagine you're at a concert. The bright white stage light is the star. Now imagine someone holds up a piece of colored glass, let's say a deep red one, in front of that light. The light that passes through it is now missing certain colors. It's been stained red. The piece of glass has left its fingerprint on the light. Now, a scientist could analyze that red light and say, aha, that piece of glass is made of a specific material that absorbs all colors except red. This is exactly what the James Webb Space Telescope and others like it do. They are the ultimate backstage passes to the cosmic concert. The star is the stage light. The planet's atmosphere is the piece of colored glass. As the planet moves in front of its star, an event called a transit, a tiny fraction of the star's light filters through the planet's thin, gaseous envelope. By the time that light completes its journey across the vastness of space and enters Webb's golden eye, it is imprinted with the secrets of that alien air. Webb doesn't see in colors the way we do. It sees in infrared, which is essentially the language of heat. It's perfectly tuned to read these chemical fingerprints. It takes this faint encoded light and spreads it out into a spectrum, a rainbow, but not a simple one. It's a rainbow with dark lines and bright bands missing from it. Each of those gaps, each of those dark lines is a barcode. One pattern of lines might scream water vapor, another might whisper carbon dioxide, and if we're incredibly cosmically lucky, one might just shout oxygen or methane. This is where the real detective work begins, because finding a gas isn't the same as finding life. You have to ask the next crucial question: what is keeping that gas there? This is the concept of chemical equilibrium, or rather, the lack of it. A dead planet, geologically inactive, will have an atmosphere that is in a kind of lazy chemical balance. The gases have all reacted with each other and with the surface rocks until they've reached a stable, sleepy state. There's no drama. It's a quiet, uneventful atmosphere. But a living planet? A living planet is a riot. It's a party constantly upsetting the chemical apple cart. And the biggest party animal of all is oxygen. Oxygen is like the hyperactive child of the periodic table. It desperately wants to react with everything. It will rust iron. It will combine with hydrogen to make water. It will break down complex organic molecules. Left to its own devices, in a geological setting, it would quickly vanish from the atmosphere, getting locked away in rocks. The only reason Earth has so much of it, a whopping 21% of our air, is because we have a biological pump working 24/7. Photosynthetic life, from the tiniest cyanobacteria to the largest redwood tree, is constantly, relentlessly pumping oxygen into the air as a waste product. It's a constant, planet-wide battle against chemistry, and life is winning. So, if we see an exoplanet with a significant amount of oxygen in its atmosphere, it's a huge, flashing neon sign that says, "Something funny is going on down here." It's not proof, but it's a very, very strong hint. Now, make that sign even brighter. Imagine we detect oxygen, and alongside it, we also detect methane. This is the cosmic equivalent of finding a smoking gun. You see, oxygen and methane are arch enemies. They hate each other. They react together very easily to form carbon dioxide and water. You cannot have significant amounts of both in an atmosphere for long unless you have separate, continuous sources constantly replenishing them. On Earth, we do. Life produces both. Animals and bacteria breathe out methane, while plants and cyanobacteria pump out oxygen. So, finding this unlikely pair coexisting in an alien atmosphere would set the astronomy world absolutely ablaze with excitement. It would suggest that not only is there life, but there might be a complex interacting biosphere with multiple different processes at work. But, and this is a very important but, a good detective never jumps to conclusions. They have to rule out all other possibilities. Could there be a non-living geological explanation for an oxygen-rich atmosphere? Perhaps. A planet that is a water world, for instance, with its entire surface covered in ocean, might build up oxygen if the intense light from its star breaks apart the water molecules in the upper atmosphere, a process called photodissociation. The lightweight hydrogen escapes into space, leaving the oxygen behind. It would be a dead, abiotic world, but it could have an oxygen atmosphere. Similarly, methane can be produced by volcanic activity, so the discovery would never be announced as aliens found. It would be a careful, meticulous process. The scientists would first confirm the detection. Then they would try to model every possible non-biological scenario that could create that atmospheric cocktail. They would look at the planet itself, its size, its orbit, the type of star it circles. Is it in the habitable zone? Is it a rocky planet? The context is everything. The more we learn about the planet, the more we can rule out those false positives. This is the beautiful, painstaking nature of modern science. It's not about quick answers. It's about building a case. The James Webb Space Telescope is the greatest detective we've ever sent into the field, but it's just the first. Future telescopes, like the planned Habitable Worlds Observatory, will be designed to directly image these pale dots, to block out the blinding light of their parent stars, and take a family portrait of these distant worlds. We might be able to see seasonal changes, the glint of sunlight off an ocean, or even the faint, telltale signature of a surface covered in something that looks very much like vegetation. So, every time you hear about a new exoplanet being discovered, know that the real work is just beginning. The light from that world is a message, a complex letter written in the language of chemistry. We are just now learning how to read it. And one day, perhaps sooner than we think, we might open a letter that doesn't just contain a description of rocks and gas, but one that has, written clearly in the barcodes of light, the unmistakable, riotous, and glorious signature of another living world. But we have to be careful. Nature can sometimes create false positives. Certain geological processes can, theoretically, produce small amounts of oxygen without life. So, the discovery would be a moment of electrifying excitement, not a confirmed announcement. It would mean we have a candidate, a place where just maybe the spark caught fire. Now let's assume the spark does catch. Life begins. For it to evolve into something more complex, it needs stability. It needs time. Lots and lots of time. This is where another fascinating concept comes in, the Great Filter. This is an idea that tries to explain the Fermi Paradox, which is, in essence, if the universe is so big and so old, and life should be common, then where is everybody? The physicist Enrico Fermi famously asked this over lunch one day in 1950, and it has haunted us ever since. The Great Filter theory suggests that there is some kind of barrier, a wall, that is incredibly difficult for life to get past. This filter could be behind us, meaning we are somehow special, we've already passed it, and that's why we exist. Perhaps the origin of life itself is the Great Filter. Maybe it really is that rare. Or perhaps the jump from simple prokaryotic cells to complex eukaryotic cells, cells with a nucleus and organelles, is the filter. On Earth, that took over 1 billion years to happen. If that is the Great Filter, then the galaxy might be filled with bacterial slime, but nothing that ever builds a radio telescope. The more unsettling possibility is that the Great Filter is ahead of us. Perhaps the development of advanced technology inevitably leads to self-destruction through nuclear war, engineered pandemics, or artificial intelligence run amok. Perhaps every civilization that reaches our stage of technological adolescence quickly snuffs itself out. This is a sobering thought. It would mean the silence of the cosmos is a graveyard, a warning. But let's be optimistic for a moment. Let's imagine a world where life not only begins but thrives, evolves, and eventually gives rise to intelligence. Not just problem-solving intelligence like a clever octopus, but a species that can manipulate its environment, develop language, build tools, and eventually look up at the stars and wonder. What would that look like? This is where we must shed our Earth-centric thinking. We are products of a very specific evolutionary path. Arboreal primates who came down from the trees, developed opposable thumbs, and learned to cooperate in large groups. Our intelligence is just one solution to the problem of survival. On another world, the dominant intelligence might not be a social, tool-using mammal. It could be a descendant of a creature more like an octopus with a distributed intelligence in its tentacles, communicating through shifting patterns of color and texture. It might be a creature that lives in the dense atmosphere of a gas giant, a vast, buoyant being like a living balloon, thinking slow, deep thoughts over centuries. Or it might not be biological at all. This is a key point. Once a species masters technology, the next evolutionary step might not be biological, but synthetic. They might upload their consciousness into machines, becoming post-biological intelligences. This could solve many problems: the frailty of the body, the short lifespan, the limitations of a biological brain. An AI could live indefinitely, travel between stars, and think in ways we cannot fathom. When we imagine advanced aliens, we might be better off imagining something more like a conscious, super-intelligent spacecraft than a humanoid with big eyes. This brings us to the concept of civilizations and how we might classify them. A Soviet astronomer named Nikolai Kardashev proposed a scale, now famous as the Kardashev scale. It's a way of measuring a civilization's technological advancement based on the amount of energy it can harness. A Type 1 civilization is a planetary civilization. They can use and store all of the energy that falls on their planet from their host star. We are not even a full Type 1 yet. We're currently at about 0.73 on the scale. We still get most of our energy from digging up dead plants and animals, fossil fuels, but we're inching our way towards mastering solar, wind, and geothermal power. A Type 2 civilization is a stellar civilization. They can harness the entire power output of their star. How could you possibly do that? The most famous theoretical concept is a Dyson sphere, a massive structure, or a swarm of structures, that encircles a star, capturing its light and converting it into usable energy. If we ever saw a star that was unusually dim in visible light but glowing brightly in infrared, the waste heat from all that captured energy, that would be a potential sign of a Type 2 civilization. It would be an engineering project of literally astronomical proportions. A Type 3 civilization is a galactic civilization. They control the energy of their entire galaxy. Their presence would be unmistakable, perhaps by the entire galaxy shining with the engineered light of countless Dyson spheres. We see no such thing. The Milky Way looks natural. This is another piece of the Fermi Paradox. If such civilizations were possible, why don't we see any evidence of their mega engineering projects? Maybe they are out there, and we just don't know how to look. Or maybe they have become so advanced that they are imperceptible to us, living in matryoshka brains, concentric Dyson spheres, where the inner layers compute at unimaginable speeds and the outer layers radiate waste heat into the cold of space. They might be living in simulated realities, having little interest in the boring physical universe outside. Or perhaps they are here, but in ways we cannot perceive, observing us like we observe animals in a forest, careful not to disturb the natural habitat. So we arrive at the cultural phenomenon of UFOs, now more formally known as UAPs, unidentified aerial phenomena. That shift in language is itself fascinating. UFO carries decades of baggage, conjuring images of little green men, flying saucers from 1950s B-movies, and tabloid headlines. UAP is a more clinical, less loaded term. It doesn't whisper aliens the moment you say it. It simply says, there is something in the sky that we, with our current knowledge, cannot identify. It's a small but important step in taking the topic seriously, and it is a cultural minefield. On one side, you have ardent believers who see a government conspiracy behind every weather balloon. On the other, you have hardened skeptics who dismiss everything out of hand, sometimes with a condescending chuckle. And in the middle, for the vast majority of us, there's a confused fascination. The key, as we navigate this, is to separate the pop culture noise from the genuine signal of mystery. We have to be sober detectives, not fervent believers or cynical debunkers. The first and most crucial point to understand is that people have always seen strange things in the sky. Long before airplanes, satellites, or drones, our ancestors looked up and witnessed phenomena they couldn't explain. In the Middle Ages, they might have been interpreted as chariots of the gods, angels, or demons. During World War II, pilots reported mysterious glowing orbs they called Foo Fighters. The human brain is a magnificent pattern recognition machine, but it has a quirk. When it lacks a ready-made explanation, it often fills in the blank with something from its own library of fears, hopes, and cultural influences. For a medieval peasant, that was a celestial sign from God. For us, in the age of science fiction, it's an interstellar spacecraft. Now let's talk about that vast majority of sightings, the ones that get explained. It's a veritable parade of the mundane once you know what you're looking at. The planet Venus. This might be the single greatest UFO imposter in history. Venus is breathtakingly bright in the dawn or evening sky, but when it's seen near the horizon, its light has to pass through many layers of our atmosphere, which acts like a wobbly lens, causing the planet to appear to twinkle, shift color, and even seem to dart around. If you're in a car driving past trees, it can create a stunning strobing effect that looks for all the world like a craft pacing you. Countless reports, including some very famous ones, have been traced back to our celestial neighbor, satellites and space debris. On a clear, dark night, you can see them, tiny, silent points of light moving steadily across the sky. These are satellites, reflecting the light of the sun. Sometimes, a tumbling piece of an old rocket body can flash irregularly, looking like a pulsating light. And when a satellite re-enters the atmosphere, it can break apart into a spectacular fiery train of debris that is often mistaken for a fleet of alien ships. Military tests. This is a huge one. The skies are a testing ground for secret technology. The U-2 and SR-71 Blackbird spy planes were responsible for a wave of UFO reports in the 50s and 60s because they flew at altitudes and speeds unknown to the public. Today, it could be advanced drones, next-generation stealth aircraft, or even projects involving holograms or electronic warfare that create illusions in the sky. If you're testing a secret plane, the last thing you're going to do is announce it. You're probably quite happy for people to think it's a UFO. Atmospheric phenomena. Our atmosphere is a dynamic and sometimes bizarre place. Ball lightning, for instance, is a poorly understood phenomenon where a glowing, spherical object of energy seems to float through the air, even passing through walls before vanishing. Sundogs are bright spots that appear on either side of the sun, caused by ice crystals in the air. St. Elmo's fire is a glowing plasma discharge that can appear on the wings of aircraft during thunderstorms. To someone unfamiliar with these effects, they can look utterly otherworldly. The prosaic and the practical. Then there are the simple explanations. Weather balloons, research balloons, large flocks of birds reflecting radar, Chinese lanterns released at a party, even kites with LED lights attached. The Humble balloon is responsible for one of the most famous UFO incidents in history, the 1947 Roswell crash, which the U.S. military eventually explained as a crashed high-altitude balloon array from a then-classified project called Mogul. So, with all these perfectly ordinary explanations, why does the mystery persist? Because of that small, stubborn percentage of cases, perhaps 5% or less, that resist all conventional explanations. And this is where the conversation gets truly interesting, especially in the modern era. We are no longer talking solely about blurry photos from a shaky hand. We are talking about incidents like the one documented by U.S. Navy pilots off the coast of San Diego in 2004, the so-called Nimitz encounter. Here you have highly trained, expert observers, the best of the best, using the most advanced sensor systems on the planet. They reported seeing a large, white, tic-tac-shaped object. It was tracked on multiple advanced radars. It was seen with their own eyes. And it behaved in ways that defy our understanding of physics. It hovered without any visible means of propulsion, then accelerated instantaneously to hypersonic speeds, moving from a standstill to over 12,000 miles per hour in the blink of an eye, making sharp, right-angle turns that would generate G-forces enough to tear any known craft and its pilot to pieces. This is the core of the modern UAP discussion. It's not about a light in the sky. It's about objects demonstrating technology that appears to be generations, if not centuries, ahead of our own. So, what are we to make of these truly unexplained cases? The scientific mind, when faced with an unknown, does not automatically leap to the most extraordinary conclusion. It methodically considers all possibilities, from the most likely to the least. So, let's lay out the possibilities for these tic-tac type events. Possibility 1. Exotic natural phenomena. This is a compelling idea. Could it be that we are witnessing a form of plasma, a trick of the light, or a type of atmospheric electricity that we simply do not understand? Perhaps these phenomena can interact with radar and infrared sensors in ways that create the illusion of a solid object performing impossible maneuvers. Our sensors are designed to filter out known clutter. What if they're occasionally fooled by something entirely new? This would be a monumental scientific discovery in itself, revealing a new chapter in atmospheric physics. Possibility 2. Advanced human technology. This is, for many, the most unsettling and likely explanation. Could this be secret technology from another nation, specifically a rival superpower? If so, it would represent a quantum leap in aerospace engineering, a leap so great it would render our current military capabilities obsolete. The idea that another country has mastered inertia-dampening, hypersonic propulsion without sonic booms, and craft that can operate seamlessly in air, water, and space is a terrifying prospect from a national security standpoint. This is undoubtedly a major driver behind the recent shift in government transparency. Not fear of aliens, but fear of a technological Pearl Harbor. Possibility 3. A non-human intelligence. This is the possibility that captures the imagination. It's the one we've been building toward in this entire essay. Could it be that we are being visited or at least observed by a civilization from another world or perhaps another dimension? The Tic Tac's performance characteristics certainly fit the bill for what we might expect from a probe capable of interstellar travel. It's important to note that this doesn't necessarily mean little gray beings are inside. It could be a fully autonomous drone, an AI-powered scout sent on a long-duration mission to survey the galaxy. If the vastness of space makes physical travel for biological beings impractical, sending resilient, self-repairing robotic probes is a perfectly logical alternative. The recent declassification of videos by the Pentagon and the establishment of official UAP task forces are not a confirmation of possibility 3. What they represent is a formal acknowledgement that the phenomenon is real, it's persistent, and it represents a potential threat to flight safety and national security. The government is essentially saying, we see this too, and we don't know what it is, and we need to find out. This has pulled the topic out of the fringe and placed it squarely in the realm of legitimate inquiry. So, where does that leave us? With a thrilling, frustrating, and absolutely necessary uncertainty. The golden rule of science remains: extraordinary claims require extraordinary evidence. A blurry video is not extraordinary evidence. A radar track is not extraordinary evidence. Even multiple sensor contacts and pilot testimonies, while compelling, are not the slam-dunk proof we need. They point to a mystery, not a solution. The extraordinary evidence required would be something tangible, something that can be tested, prodded, and analyzed by the entire global scientific community. A piece of the craft. A material with an isotopic ratio that doesn't exist in nature. A technology that operates on principles unknown to our physics. Until we have that, until we have a piece of the puzzle that we can hold in our hands and that unequivocally points to a non-human origin, the scientific consensus will rightly remain. We have no conclusive proof of visitation, but the search has changed. It is no longer just about looking out at the stars. It is also about looking up into our own skies with a new, more serious, and more sophisticated gaze. The mystery of UAPs is a reminder that our understanding of the world and the universe is still incomplete. It humbles us. It tells us that there are still wonders and terrors just beyond the edge of our map, labeled only with the words, "Here be dragons." And whether those dragons turn out to be storms of plasma, the secret weapons of our rivals, or something far, far stranger, the journey to find out is one of the most exciting detective stories of our time. But SETI is evolving. It's not just about radio anymore. We could look for laser pulses, signs of massive engineering, or even technosignatures, like industrial pollution in an exoplanet's atmosphere. The search is broadening, and there's another approach, METI, or Messaging Extraterrestrial Intelligence. This is the active side. Instead of just listening, we broadcast a message, announcing our presence to the cosmos. This is far more controversial. Some, like the late Stephen Hawking, warned that it could be incredibly dangerous, like shouting in a jungle we don't understand. An advanced civilization might not see us as equals, but as a resource or as pests. Others argue that any civilization advanced enough to travel between stars would already know we are here from our television and radio broadcasts, which have been leaking into space for the better part of a century, creating an expanding bubble of I Love Lucy and news broadcasts that now extends over 100 light-years from Earth. Perhaps the silence is not a sign of absence, but of distance and time. Space is big. Really, really big. The distances between stars are so immense that they pose a fundamental barrier to any kind of physical contact. The nearest star system, Alpha Centauri, is over 4 light-years away. That means even if we could travel at the speed of light, which, according to our current understanding of physics, is impossible for anything with mass, it would still take over 4 years to get there. A more realistic, but still wildly ambitious spacecraft using nuclear pulse propulsion might take centuries. An interstellar voyage is a generational undertaking, a commitment spanning lifetimes. So maybe civilizations are out there, but they are isolated islands in a vast ocean. They might broadcast for a while, but if no answer comes back for 1,000 years, they might give up or turn inward. The overlapping lifetimes of technological civilizations that are close enough to talk to each other might be vanishingly small. We might be like ships passing in the night, separated by an ocean of space and a gulf of time. Or perhaps we are looking at the problem all wrong. What if life is not just common, but a fundamental property of the universe, as inherent as gravity or nuclear forces? This is the hypothesis of panspermia. It's a grand and elegant idea that suggests the building blocks of life, or even life itself in a dormant, spore-like state, are common throughout the cosmos, hitchhiking on the natural taxis of the universe, asteroids, comets, and the dust grains that drift between the stars. Think of it as cosmic pollination. A comet, rich in water and organic molecules, might be buzzing from star system to star system like a bee, and if it passes through a fertile planetary system, it might just deposit its precious cargo. Let's break down how this could actually work, because it sounds like science fiction, but the physics is surprisingly sound. Imagine a world, let's call it Planet A warm, wet, young world where life has just begun. It's teeming with simple, resilient microbes. Then, disaster strikes. A massive asteroid slams into Planet A. The impact is catastrophic. It vaporizes rock, sends tsunamis racing across the globe, and blasts billions of tons of material, including some of those tough little microbes, out into space. Now these microbes are trapped inside chunks of their home planet, shielded from the worst of space radiation within their rocky carapaces. They are in a state of suspended animation, a deep, deep sleep. This chunk of rock becomes a tiny, unintended spaceship. For millions, even hundreds of millions of years, it drifts through the silent, cold black. The microbes inside, creatures like our own earthly extremophiles that can survive in boiling vents or frozen tundra, are in their element, or rather their lack of it. They can withstand the vacuum and the cold. Then, finally, the gravitational pull of a new star, a new solar system, tugs on this wandering rock. It falls inward, and by a fortunate chance, it lands on another young, promising world. Planet B. The heat of entry might sterilize the outside, but the interior of the rock remains cool, protecting its tiny passengers. It crashes into a warm, salty ocean. The rock slowly erodes, and the microbes, waking from their million-year slumber, find themselves in a new paradise, rich with the ingredients they need. They begin to multiply. Life on Planet B begins, but it didn't start there. It was an immigrant. Now here's the thrilling part. We might be the products of this very process. We know that in the early solar system, Mars was a promising candidate for life. It was warmer, it had a thicker atmosphere, and it had vast oceans and rivers. We also know that because Mars is smaller and has less gravity, it's much easier for impact debris to be ejected into space and eventually find its way to Earth. Meteorites from Mars have been found here on Earth, confirmed by the unique chemical signature of the Martian atmosphere trapped inside them. So the highway between Mars and Earth was very much open in those early violent days. It is entirely plausible, and many respected scientists think it's even likely, that life originated on Mars first and then seeded Earth. You, me, every person, every bird, every blade of grass, we might all be descendants of Martians. It's a humbling and wonderfully unifying thought. But, and this is the crucial point the text makes, panspermia doesn't actually solve the ultimate mystery. It just moves it. It tells us how life might have gotten here, but it doesn't tell us how it started in the first place. Whether the spark of abiogenesis happened in a Martian ocean or an earthly tidal pool, it still had to happen somewhere. The miracle of that first self-replicating molecule is not explained by panspermia, it's just given a bigger stage. However, what it powerfully suggests is that if life can hop from one world to another so easily, then it might not need to start from scratch on every single habitable planet. Once it gets a foothold in a single solar system, it could, in theory, spread to every other suitable world in that system, like moss spreading across a damp, rocky hill. The entire solar system becomes a single, interconnected biological zone. This dramatically increases the chances that life is widespread because it only needs to win the abiogenesis lottery once per star system, not once per planet. Now let's take that already big idea and stretch it to its absolute limit into a realm that is less about testable science and more about a profound philosophical and spiritual possibility. What if we're still thinking too small? What if life isn't just something that happens within the universe? What if the universe itself is alive? This is a concept that has echoed through human thought for millennia, from the animistic beliefs of ancient cultures who saw spirits in rivers and trees, to the philosophies of the Greeks. But now, we can look at it through the lens of modern physics and complexity. We tend to think of consciousness as something that emerged very late in the game, a quirky byproduct of a complex brain that evolved for survival. But what if that's backwards? What if consciousness is a fundamental property, a base layer of reality, like space and time and matter? What if it's not that brains produce consciousness, but that they tap into it? That they are complex receivers, like radios, tuning into a signal that has always been there? Think about the atom, the building block of everything. A typical atom is overwhelmingly empty space. If you enlarged an atom to the size of a cathedral, the nucleus would be a mere grain of sand in the center, and the electrons would be other specks of dust whizzing around in the vast dome. So, what is all that empty space? Is it truly nothing? Or is it a field of potential, a vibrating, energetic substrate that connects everything? The strange world of quantum mechanics already tells us that particles can be connected across vast distances, instantly influencing each other, a phenomenon Einstein called spooky action at a distance. What if that spookiness is a hint of a deeper, interconnected reality? In this view, the entire cosmos, every galaxy, every star, every planet, every rock, and every one of us is part of a single, vast, conscious entity. We are not separate things living in a universe. We are localized expressions of the universe. Your body is made of atoms, forged in stars. The water you drink has been through oceans and clouds for billions of years. You are the universe, gathered together for a brief moment into a form that can think and feel and wonder. And so is every other potential being out there. This makes the quest to find extraterrestrial intelligence something far more intimate and profound. It's not us, a separate entity, searching for another separate entity. It is the universe, through us, seeking to know other parts of itself. It is the cosmos looking at itself in the mirror. When we gaze at the stars, we are the universe becoming self-aware. When we send out probes and signals, we are the universe reaching out to touch its own edges. And if we were to ever receive an answer, it wouldn't be a conversation between two strangers, but something more like a family reunion across the vastness of space and time. This idea, often called panpsychism, is of course not proven. It may never be. It exists in the beautiful space where science, philosophy, and spirituality meet. But it offers a powerful and poetic perspective on our place in the grand scheme. It suggests that the loneliness we sometimes feel when looking into the cosmic dark might be an illusion. We are not alone because we cannot be alone. We are inextricably woven into the fabric of a reality that is, at its very heart, awake and aware. The silence from the cosmos, then, is not an empty silence. It is the quiet of a sleeping giant, of which we are a dreaming part. And our search for others is the dream becoming lucid, the first stirrings of a wakefulness that may one day encompass the stars. But let's come back down to Earth, to the practical, tangible search. Right now in our own solar system, we are hunting for life. Not little green men, but microbes. Mars is the prime candidate. Once, billions of years ago, it had rivers, lakes, and perhaps even a vast ocean. The Perseverance rover is right now, as we speak, drilling into the rocks of an ancient river delta in Jezero Crater, collecting samples that may contain fossilized evidence of past Martian life. Future missions will bring those samples back to Earth for analysis. It will be one of the most important scientific experiments in history. If we find that life arose independently on Mars, a world right next door, it would be a monumental discovery. It would tell us that the universe is likely buzzing with life. We would know that we are not alone in the most profound sense, and Mars isn't the only candidate. Far out in the cold, dark reaches of the solar system, there are moons with hidden interior oceans. Jupiter's moon Europa is a cracked, icy world with a global saltwater ocean beneath its frozen crust, kept liquid by the gravitational tug-of-war with Jupiter. The Cassini spacecraft showed us plumes of water vapor erupting from the south pole of Saturn's moon Enceladus, a tiny world with a massive subsurface ocean. And Saturn's largest moon, Titan, is a bizarre alien place with lakes and rivers not of water, but of liquid methane and ethane. Could life, a truly alien life with a different biochemistry, exist in those methane seas? Could it swim in the dark oceans of Europa? We are designing probes to find out. A mission to Europa, aptly named Europa Clipper, will soon fly through its plumes, analyzing the chemistry of that hidden ocean. We are, for the first time, on the verge of being able to answer the question of whether we are alone, not in the distant galaxy, but in our own cosmic backyard. The implications of discovering life, any life, beyond Earth would be earth-shattering. It would complete the Copernican revolution. Copernicus told us we are not the center of the universe. Darwin told us we are not separate from the animal kingdom. The discovery of extraterrestrial life would tell us we are not the only life in the cosmos. It would redefine our place in the universe. It would have philosophical, theological, and cultural repercussions that would ripple through human society for generations. And if we were to discover intelligent life, to receive a confirmed, decipherable signal from the stars, it would be the single most important event in human history. All of our petty squabbles, our borders, our conflicts, would suddenly be seen in a new cosmic context. We would be one humanity, faced with the reality that we are not the only thinking beings in the void. It would be a moment of terrifying vulnerability and exhilarating possibility. What would they be like? What would they know? What could they teach us? The knowledge of an older, wiser civilization could help us solve our greatest problems: disease, poverty, energy, even our own self-destructive tendencies. Or it could present a threat we cannot comprehend. But perhaps the most beautiful outcome of this grand quest is what it tells us about ourselves. The drive to explore, to know, to reach out is one of the most noble and defining characteristics of humanity. We are a species born on a small rock, gifted with consciousness, and cursed with the knowledge of our own insignificance. And yet, we refuse to accept it. We build telescopes to see to the edge of time. We send robots to other worlds. We listen to the silence, hoping for a whisper. This search in itself is a testament to the human spirit. So, are we alone? The honest scientific answer is, we don't know. The universe has not yet given up its secret, but the evidence is mounting that the conditions for life are common. The ingredients are everywhere. The real estate is plentiful. It feels in our bones that we cannot be the only ones. The silence is not evidence of absence. It is a challenge. It is a puzzle we are only just beginning to solve. The story is not over. It is being written right now by astronomers peering through telescopes, by biologists studying extremophiles in the harshest environments on Earth, by engineers designing probes for distant worlds, and by you, looking up at that star and wondering. The search for life beyond Earth is a journey that binds us all together. It is a question that has haunted us since we first gazed at the night sky, and it is a quest that will define our future as a species. We are the universe become conscious, looking back at itself and asking, is anybody there? And in that asking, in that relentless, hopeful, beautiful search, we may just find the most important answer of all, that we are part of something greater, a cosmic tapestry of matter and energy, and just maybe, life and mind, stretching across the vast, star-dusted expanse of space and time. The conversation has only just begun, and the next chapter, perhaps, is yours to write. Good night, and have a deep, calm sleep. So